Good evening, welcome in RNQ Easino classes. Block number 3 Contemporary Cosmological Theories. Unit 1 Theories of Relativity. Unit 1 1.1 Introduction. The advent of the theory of the relativity and of the quantum mechanics has revolutionized the whole domain of science. They question some of the age-old concepts such as absolute motion, absolute space, absolute mass, wave nature, or particles, unlimited perfectibility of experimental results, etc. They brought in certain radically new concepts and gave new insights into several baffling phenomena in nature. Towards the end of the last century, it became abundantly clear to scientists that the real trouble sports in scientific inquiry were in the Pathomes defects in intergalactic space. At the other end, quantum mechanics arose in an effort to answer the problems having in the subatomic world and relativity in the ultragent, ultragent and ultrafast world. To show the pervasive importance and relevance of relativity in theoretical science up today we give a few questions from the leading writers. Thus Margini writes, in fact the theory is now क्यों चला रहा है is now so well corroborated by experience and the assimilations into the whole of the modern physics that it's Daniel, it's almost unthinkable. The physicist is impressed not solely by its for long empirical verifications, but above all by the intrinsic beauty of its conception, which predisposes the discriminating mind for acceptance even if there were no experimental evidence for the theory at all. Again, Horton relativity has profoundly changed the whole of physics by the analysis of the fundamental concept of space and time, of mass and of force. It has given a new orientation not only to science but also to our approach to philosophic problems in general. Before Einstein, physicists were confident which they understood distance, time and mass. They believed any skilled person could measure distance with a ruler, tell time with a clock, weigh mass with a scale, and get the true values. With his theory of special relativity, Einstein proved that this was wrong, that there were no true values, and he shook the every foundations of science. Einstein developed two theories of relativity: special relativity and general relativity. Special relativity, published in 1905, covers only special simple situations, those in which there are no forces. It was followed 10 years later by general relativity, which includes Einstein's theory of gravity and is the more complex theory. 1.2 The theory of relativity. In everyday language, we can say that a relativity is a theory which holds that concepts like motion, length, time, mass, etc. are not absolute. They make sense only when referred to a frame of reference. Thus, an astronaut of mass, say 80 kg, on the surface of the Earth, first frame of reference, may have a mass of 100 kg, while inside a fast-moving rocket, second frame of reference. A different definition is given by Eddington and attitude, which leads to the conclusions that we observe only relations between physical entities. Special and general theory of relativity. Einstein published his theory in two papers, in one 1905 and other 1916. The forms of the special theory and his the and this deals with only uniform motion of bodies. The second is called the general theory, and this deal with all moving bodies, including those with non-uniform velocities, that is accelerated bodies. Postulates of the special theory of relativity. Einstein explained the negative result of experiment in the form of two postulates. Postulates first, it is impossible to determine absolute motion by experiment whatever so in the exist. Hence, the phenomena of nature will be the same of for two observers who move with may uniform velocity whatever relativity to one another. Putting it in another way, we can say that uniform motion does not affect physical laws. That general laws of physics are the same in all systems moving uniformly with respect to each other in a straight line. This is called the systems moving uniformly with this is called the principle of relativity, from which the theory gets its name. Postulate second, the velocity of light is a constant absolute quantity. It is independent of the motion of the source of the or of the observer. Implications and consequences of the postulates. It is impossible to measure the uniform motions of a body by observing events taking place within the body. According to the first postulates, all natural events are unaffected by uniform motion. So by observing them from within the body moving with uniform velocity, we can't measure its velocity. Consider a train moving with constant speed. Everything inside it happens as through it is motionless. 1.3 relativity of motion, length times simultaneously. We must give up the classical platform of an immobile framework of space. It is meaningless to talk of absolute rest. All motions is relative in snag sense only when referred to a frame of reference as an illustration. Consider a station master as the platform and an engine driver in a moving train. The station master will say that the engine driver is moving with respect to him. The engine driver, on the other hand, will say that the station's master is moving with respect to him. And this engine relativity and length is not something absolute in the sense that it has the same value everywhere. The stationary observer will notice the contractions, but the observer in the moving frame will not be able to measure any contractions because his scale also will have contracted by the same amount. Thus, it follows that it is meaningless to speak of length without specifying the frame of reference, without specifying whether the length is taken with respect to a moving observer or a stationary observer. Contraction is perfectly reciprocal. Each observer notices contraction in the system of the other. It is not a construction of bodies but of the measurement of bodies of length, where length is not an intrinsic property of the body of conception be associated with the body. Relativity of time. कैसे लगा है बाबू को यहाँ पे? Relativity of time. We must give up the classical notion of steady univariant on a in inexorable universal time flow steaming from the infinite past to the infinite future. In a moving frame, time slows down to observe moving with different uniform velocities will have different values to the durations of. And even Newton assumed time was absolute and universal. He assumed time ran its own interesting rate, unaffected by anything else, flowing at the same rate everywhere and always. But Einstein showed that all this was wrong. Time is relative. There is no one true time. Time runs at different rates in different inertial frames. Different clocks will inevitably measure different different times. Let us try to see why it is true. Time is our way of measuring how rapidly things change. If nothing ever changed, time would be a meaningless concept. Every clock counts the number of time something changes. In truth it is time itself that appears to us to be slower in a moving frame. This is called time dilation. Hence, according to relativity, there is no absolute before and after absolute topological time is ruled out. This means that there is no absolute past, present, future applicable to the cosmos as a whole. Also, there is no absolute duration. This rule is out absolute metric time. Space-time and four-dimensional continuum. Herman Hermann Minkowski realized Einstein's theory changed our understanding of the geometry of our universe. The three-dimensional space can no longer be considered distinct from time to space, and time must be viewed as a combined four-dimensional entity that Minkowski named space. Time in a four-dimensional space, time points are called events, and four questions are required to specify an event such as latitude, longitude, attitude, and time. Time measurements and normal three-dimensional distance measurements are relatively different from different observers, but the distance between two events in four-dimensional space-time is invariant. The same for all relating system expressing certain general features of physical objects. Thus, they describe the world in an orderly way. It is true that they are constructs of the mind, but they are not pure. They're not pure empty concepts. They are concepts fit to describe the physical world in Hans Richard Welling's walls. This conceptual system describes relations holding between physical objects in addition. These relations formulate physical laws of great generality, determining some fundamental features of the physical world. Space and time have as much reality as, say, he relation father of the Newtonian forces of attractions. Thus, the relations we talk of our objective relation. स्पेलिंग के साथ पढ़, धीरे धीरे पढ़, अभी पढ़ यार। Isaac Newton 2.3 Introducing Quantum Mechanics. Isaac Newton thought the light was a stream of particles. Thomas Young thought it was a wave. Hey, most people at the turn of the century thought of light as a wave. In 1900, Max Planck found that he could explain the way hot bodies radiate energy only if he assumed that energy occurred as packets. He assumed that his equations were simply tricks that the mathematics and called these packets of energy quanta. The quotations were useful, but the underlying ideas were not taken seriously. In 1905, Albert Einstein published 3 scientific papers, any one of which was the Mark of a genius. The first was part one of his theory of relativity. The second proved the existence of atoms from direct observations, an effect called Brownian motion. The third paper is the relevant one for this easy. In this paper, he applied Planck's quantum idea of 1900 to explain the पूरा हम लोग को पॉइंट की तरफ लिखा और ये papers in one which was the mark of genius. The first was part one of his theory of relativity. The second proved the existence of atoms from direct observation, an effect called Brownian motion. The third paper is the relevant one for this essay. In this paper, he applied Planck's quantum idea of 1900 to explain the photoelectric effect. These quanta were now being utilized to explain two previously unexplainable phenomena. However, its quanta were real, was light, a wave, or a particle. It was as if in some experiment refraction diffraction light was clearly a wave in others black body radiation. The photoelectric effect, it was a particle. This effect was strange and was known as wave particle duality till 2009. In 1912, Louis de Broglie suggested that if energy could behave as both particles and waves, perhaps matter could also. He nearly didn't get his PhD for that ridiculous suggestion. He produced the mathematics. He predicated that under the light conditions, a beam of electrons, clearly matter made of particles, might so have properties. Surprisingly, when the experiment was performed, a beam of electrons was found to direct just like a wave would have done. That was it. It looked like energy and matter could both exhibit wave-particle duality. It appeared that a moving particle had a wavelength. Niels Bohr decided to work out the wavelength of an electron moving around the nucleus of an atom. He found that for an electron to have a stable orbit, the orbit had to include a whole number of the electrons. Wave orbits that include fractions of waves were impossible, so the electron could not inhabit them. In other words, an electron could have a stable orbit so that it would not lose energy and spiral into the nucleus. If an electron absorbed or radiated energy, it would do so in discrete amounts so that it would move to another stable orbit. The analogy is a staircase. You can only stand on the steps, not in the region between steps. So these quantum ideas explain two things: why atoms were stable and why atoms absorbed or emitted energy is selected wavelengths. Bohr used his ideas to predicate what energy could be radiated from different atoms. His theories corresponded with observation. In 1925, Erwin Schrödinger and Werner Heisenberg separately worked out the mathematics of quantum mechanics. Using this new theory, scientists could understand the behavior of atoms and subatomic particles. The wave particle duality concept is true for both matter and energy. The position of particle like electron is given by a probability. Electrons exist in energy states when they observe energy. They observe a whole number of quanta disappear, appearing at a different energy state. Gone is the idea of little ball like particles. The orbit of an electron is a cloud of probability around the nucleus. Style 2009. Another quantum effect is the famous uncertainty principle. This implies that there is a built-in uncertainty in the universe. It is possible for something to be created out of nothing given enough time. On a subatomic level, it is impossible to pinpoint things down to an infinite precision, and not because of any technological feelings. This is a constraint of the universe itself. A zero energy is impossible since it would be a imprecise state. This is the reason that nothing can be cooled below 273 degrees C. Absolute zero, an atom must retain at least one quantum of energy, and this keeps it from cooling below absolute zero. This means that nothing can ever be. At least quantum effects are not noticeable in the macro world. They only become important as one approaches the dimensions of the atom. Tal 2009. First and Young. A, a tumultuous series of events occurred within the 3-year period from January 1925 to January 1928, culminating in quantum revelation. Believed some of them main events. Wolfgang Pauli proposed the exclusion principle, providing a theoretical basis for the periodic table. Werner Heisenberg, with Max Born and Pascual Jordan, discovered matrix mechanics, the first vision of quantum mechanics. The historical goal of understanding electron motion within atoms was abandoned in favor of a systematic method of organizing observable spectral lines. Erwin Schrödinger invented wave mechanics, a second form of quantum mechanics in which the state of a system is described by a wave function. The solution of Schrödinger's equation, matrix mechanics as wave mechanics, apparently incompatible, were soon to be equivalent. Electrons were shown to obey a new type of statistical law, Fermi direct statistics. It was recognized that all particles obey either Fermi direct statistics or Bose-Einstein statistics, and that the two classes have fundamentally different properties. Heisenberg enunciated the uncertainty principle. Paul M. Dirac developed the relativistic wave equation for the electron that explained electron spin and predicted animator. Dirac laid the foundations of quantum field theory by providing a quantum description of the electromagnetic field. Bohr announced the complementarity principle, a philosophical principle that helps to resolve apparent paradoxes of quantum theory, particularly wave-particle duality. The principal players in the creations of quantum theory were very young. In 1925, Pauli was 25 years old. Heisenberg and Enrico Fermi were 24, and Dirac and Jordan were 23. Schrödinger at age 36 was a late bloomer. Born and Bohr were older still, and it is significant that their contributions were largely interpretive. The profoundly radical nature of the intellectual achievement is revealed by Einstein's reaction, having invented some of the key concepts that led to quantum theory. Einstein rejected it. His paper on Bose-Einstein statistics was his last contributions of quantum physics, and his last significant contributions to physics. That a new generation of physics was needed to create quantum mechanics is hardly surprising. Lord Kelvin described why in a letter to Bohr congratulating him on his 1913 paper on hydrogen. He said that there was much truth in Bohr's paper, but he would never understand it himself. Kelvin recognized that radical. से पढ़ के सुना ना, उसका बोल रही है पढ़ के सुना ना। आंटी कौन बोला था सुबह पढ़ने के लिए? कौन टेबल? क्या लिख रहे हो? पढ़ के लिखो। Within a span of 3 years, the revelations was finished, and the foundation of quantum. Mechanics were essentially complete. The main actors were very young and energetic minds in the 20s, Kepler and Jacques. Controversy and confusion. Alongside these advances, however, fierce debates were taking place on the interpretation and validity of quantum mechanics. Foremost among the protagonists were Bohr and Heisenberg, who embraced the new theory, and Einstein and Schrödinger, who were dissatisfied to appreciate the reasons for such turmoil. One needs to understand some of the key features of quantum theory, which we summarize here. Kepler and Jacques 2000. Fundamental descriptions: the wave function, the behavior of system in quantum mechanics is described by Schrödinger equation. The solution to Schrödinger's equation are now to wave functions. The complete knowledge of a system is described by its wave function, and from the wave function one can calculate the possible values of every observable quantity. The probability of finding an electron in a given volume of space are proportional to the square of the magnitude of the wave function. Consequently, the locations of the particle is spread out over the volume of the wave functions. The momentum of a particle depends on the slope of the wave functions. The greater the slope, the higher the momentum, because the slope varies from place to place. Momentum is also spread out. The need of abandon a classical picture in which positions and velocity can be determined with arbitrary accuracy in favor of a blurred picture of probabilities is at the heart of quantum mechanics. Kepler and Jacques 2000. Waves can interfere. The heights of a waves can add or subtract depending on their relative phase. Where the amplitudes are in phase, they add. Where they are out of phase, they subtract. Of a wave can follow several paths from source to receiver. As a light wave undergoing to slight interference, then the illuminations will generally display interference fringe particles. Solving wave equations will do likewise as in electron diffractions. The analogy seems reasonable until one inquiries, but the nature of the wave or wave is generally thought of as a disturbance in medium. In quantum mechanics, there is no medium, and in a sense, there is no wave, as the wave function of fundamentally a statement of our knowledge of a system. Kepler and Jacques 2000. Questions such as what a wave function really is and what is meant by making a measurement were intensely debated in the early years. By 1930, however, a more or less standard interpretations of quantum mechanics had been developed by Bohr and his colleagues. Matter and events and reconciliations of a wave-like and practical-like natures of things through debates its principles until Einstein's death in 1955. Nevertheless, the nature of quantum theory continues to attract attention because of the fascinations with what is sometimes described as quantum weirdness. Kleppner and Jackie 2000 different हाँ
सुई के देखो पड़ता है कैसा
ए ए बड़की छोरी
मोन के को तो नीचे से बैठबे नहीं करे कल
देखो क्या पढ़ने में भी घंटा ला रहा है क्या 1 घंटा अच्छे से बैठ तू अच्छे से बैठ मेरे जैसे क्या बैठ गई है बैठ अच्छे से फोल्ड करके पैर और नीचे रख बुक पैर के ऊपर नहीं रखते नीचे बुक रख
तू तो सुधार लेने छी तो कहां से सुधार
और तू भी ऐसा मत पैर रख पैर अच्छे से ऐसा रख और बुक नीचे रख अभी लिख बुक नीचे रख के लिख
बाबू पढ़ते 12 बजा दी
Differences from classical physics. Now that we have some ideas of the basic quantum mechanics, we can try to compare it with classical mechanics. The main difference of the new theory from classical physics could be summed up as follows. In classical mechanics, a particle can have any energy and any speed. In quantum mechanics, these quantities are quantized. This means that a particle in a quantum system can only have certain values for its energy and certain values for its speed or momentum. Newton's law allow one in principle to determine the exact location and velocity of a particle at some future time. Quantum mechanics, on the other hand, one determines the probability of a particle to be in a certain location with a certain velocity at some future time. The probabilistic nature of quantum mechanics makes it very different from classical mechanics. Quantum mechanics incorporates what is known as the Heisenberg uncertainty principle. The principle states that one can't know the location and velocity of quantum particle to infinite accuracy. The better you know a particle's locations, the more uncertain you must be about its velocity, and vice versa in practice the level. खाने आते थे को हाँ तू खा
देखो कैसा चिढ़ा के खिया खा रहा है बोलो एक बार और बोलो दे बाबू दीदी के मुंह में दियो दीदी के मुंह में खिया दियो दीदी के
एक दो
अपना दीदी के ओए दीदी के
मेरे को खिला दो मैं को खिला दो
बाबू खिला दे दीदी को दे दे अगर आप बोले ना ऐसा दे
खिला दे
बात ये दे
खा ले बैठ जा बैठ के खा बैठ
मुंह में दे के अपने खा ले
तू क्यों इतना ये चिल्ला रही है अरे कैसा तरीका है पढ़ने का तुम लोग का होमवर्क हो जाएगा ना एक आना इधर तुम लोग का टेस्ट लूंगी लिख के हो गया तो तुम लोग याद करके हो जाता है ना हाँ तो टेस्ट लूंगी हाँ आता नहीं तो मैं देखूंगी तू अपना कर uncertainty that is required is so small that it is only noticeable when you are declining very tiny things like atoms. This is why we can't see the effects of the uncertainty principle in our daily lives. Quantum mechanics permits where the called superpositions of states. This means that a quantum particle can be in two different states at the same time. For instance, a particle can actually be located in two different places at one time. This is centrally not possible in classical mechanics. Quantum mechanics systems can exhibit a number of other very interesting features such as tunneling and entanglement. These features also represent significant differences between classical and quantum mechanics, although they will not be as important in our discussions of quantum. Choose time दीदी हो गया टाइम बर्लेक 2000 अच्छे से पढ़ ले, गलत नहीं होना चाहिए एक भी. टीम बर्लेक 2010. That is a pretty brief introduction to the ideas of quantum mechanics, and many important features have been skipped, but the ideas presented above should make it clear that quantum mechanics is very different from classical Newtonian mechanics. Very wideness of quantum mechanics. Already noted, the field of quantum mechanics concerns the descriptions of phenomena on small scales where classical physics breaks down. The biggest difference between the classical and microscopic realm is that the quantum world can't be perceived directly, but rather through the use of instruments and key assumptions to quantum physics is that quantum mechanical principle must reduce to a Newtonian principle at the microscopic level. There is a continuity between quantum and Newton mechanics. Quantum mechanics was capable of bringing order to the uncertainty to the microscopic world by treatment of the wave functions with new मैथमेटिक्स की. तुम मारते नहीं हो ना, इसलिए तुम लोग का ये होता है. की टू दिस आइडिया was the fact. हो गया तेरा छोटी, हो गया. खा ले कुछ चना, इसका टेस्ट लो. ले रही हूँ, एक मिनट. तभी तक पढ़ो अच्छे से, एकदम राइट होना चाहिए सब जो भी पूछूंगी. पढ़ तभी तक. हाँ, स्पेलिंग देना है. आंटी भी स्पेलिंग के साथ ही लेती है ना. मेरा हो गया. हाँ हो गया तो अच्छे से पढ़, एक भी मिस्टेक. स्टोन स्पेलिंग कर. एस पी. तो पी क्यों बोल रही है? STONE. वैर स्पेलिंग कर. VAN. वैर अभी जो पढ़ रही है उसमें वैर, भैन नहीं, वैर वेयर. दोनों मूर्ति का कुछ नहीं हुआ है पढ़ के. वो मैं स्पेलिंग के साथ लूंगी जल्दी. तुम्हारा लूंगी पहले. तुम पढ़ो, उसका जाने दो, वो तो बांटी देखेगी. तुम पढ़ो पहले. अच्छा उसका लेने बोल रहे हो. हाँ ठीक है, उसका पढ़ो तुम पूरा, फिर लूंगी मैं. ए पढ़ तू भी. By treatment of the wave functions with new mathematics, key to this idea was the fact that relative probabilities of different possible states are still determined by laws. Thus, there is a difference between the role of chance in quantum mechanics and the unrestricted choice of lossless universes. Every quantum particle is characterized by a wave function. In 1925, Erwin Schrödinger developed the differential equation which describes the evaluation of these wave functions by using Schrödinger equations. Hey! Scientists can find the wave functions which solves a particular problem in quantum mechanics. Unfortunately, it is usually impossible to find an exact solution to the equation, so certain assumptions. क्या हुआ?
ये कीड़ा है ना उसके लिए
Scientists can find the wave function which solves a particular problem in quantum mechanics. Unfortunately, it is usually impossible to find an exact solution to the equation, so certain assumptions are used in order to obtain the approximate answer for the particular problem. However, some its findings and खा ना चुपचाप findings, the principles are distinctly counterintuitive and friendly difficult to explain in simple language without resorting to complex mathematics way beyond the comfort level of most people, myself included. This situation
वो कीड़ा है ना उसके
last century or so, that some elements of it are still not well understood by the scientists themselves, and that some of the bizarre behavior it predicts appears to fly in face of what we have come to think of as common sense. Richard Feynman, winner of the 1965 Nobel Prize of Physics and arguably one of the greatest physics of the post-war era unapologetically frank. I think I can safely say that nobody understands quantum mechanics. Niels Bohr and the main pioneers of quantum theory claimed that anyone who is not shocked by quantum theory has not understand it. UP 2001 below we have two implications of quantum mechanics that makes it bad or strange. Schrödinger's cat. In 1935, Schrödinger, who was responsible for formulating much of the wave mechanics in quantum physics, published an essay describing. ए पढ़ना कितना बक बक मुंह चला रही है हो गया पढ़ के तेरा
भैया देखो ना या भोग लेना या देखो ना या नहीं पहर के सुनेल के त दुनु त देखो ना की करे किताब के बड़का बड़का
अभी मम्मी मारेगी ना ऐसा
ऐसे जना बरनी लोग लगले त नहीं टक्के नहीं लग
describe the conceptual problems of quantum mechanics. A brief paragraph in this essay describes the now famous cat paradox. क्या हुआ पढ़ना ए क्या हुआ क्या हुआ ऐसा ऐसा क्या
एक बार बता दे
क्या मैं धीरे पढ़ू धीरे धीरे पढ़ रही है
जब बता दे वो बोल रही क्या मैं ऐसो
One can even set up quite radical cases where quantum physics rebels against common sense. For example, consider a cat is penned up in a steel chamber along with the following diabolical device which must be secured against direct interference by the cat. In the device is a geyser countered with a teeny bit of radioactive substance so much that perhaps in the course of 1 hour only one of the atoms decays, but also with equal probability perhaps none. If the decay happens, the counter tube decides the through or really releases a hammer which shatters a small flask of hydrochloric acid. If one has left this entire system to itself for an hour, one would say that the cat still lives. It Meanwhile, no atom was decayed. The first atomic decay would have poisoned it. The Webb functions for the entire system would express this by having in it the living and the dead cat mixed or spread out in the equal parts UP 2001. It is typical of these cases that an indeterminacy originally restricted to the atomic domain becomes transformed in microscopic indeterminacy, which can then be resolved by direct observation that prevents us from so native accepting as valid a blood model for representing reality in itself. It would not embody anything unclear or contradictory. There is a difference between a say or out of focus photograph and a snapshot of clouds and fog banks. We know that superpositions of possible outcomes must exist simultaneously at a microscopic level because we can observe interference effects from these. We know, at least most of us know, that the cat in this box is dead, alive, or dying, and not in a spread out state between the alternatives. When and how does the model of many microscopic possibilities resolve itself into a particular microscopic state? When and how does the fog bank of microscopic possibilities transform itself to the blurred picture we have of a definite microscopic state? That is the collapse of the Webb function problem. And Schrödinger's cat is a simple and elegant explanation of that problem. UV 2000 and conclusions for experiment of the Schrödinger's cat. The paradox is perhaps such that a quantum event determines if a cat is killed or not. From a quantum perspective, the whole system state is tied to the wave functions of the quantum event, that is, the cat is both dead and alive at the same time. The paradox, in some sense, 1 minute, is not a paradox but instead points out the tension between the microscopic and microscopic worlds and the importance of the observed and quantum object exist in superposition many states as shown by interference. The observer or measurement collapse the Webb function. ए उसको उधर उठा के बेटा हग रहा है.
हमारा
पढ़ो जल्दी. अभी
क्या करेगा, क्या मालूम. मैं अभी जाऊंगी ना गाँव. अभी अगला महीना तक जाओगी ना, दोनों को छोड़ के आज करिए, हम तीनों को आ जाएंगे और दोनों
हाँ, अच्छा होएगा, गांव में ही छोड़ दो.
हाँ,
क्यों छोड़?
देखती कितना माथा पागल करती है दोनों. वहाँ पे सबको मिल के मारेगी ना, बराबर हुए. ये आएगी से मारेगी. जिससे दादी उसका झगड़ा कितना लोग से करेगा, दादी उसका.
कौन है? ए! कोई आया है क्या मेरे घर पे?
हाँ, कोई मोटा.
उसको इधर नीचे रख. जानबूझ के इन लोग कर रहे, उसको नीचे रखो. जानबूझ के नाटक कर रहे.
हाँ, जानबूझ के करता है ना कि वो हमारा मम्मी का कुछ नहीं बोलती है ना.
अरे यार, हाँ, पैर लगा.
हटा ना प्यार करने बाहर. नाच जे दुनू कर रही है. थोड़ा के कर रहे हैं दुनू. बोले पीछे पगले आ रही
हो गया पढ़ के? Quantum tunneling refers to the phenomena of particles' ability to penetrate energy barriers within electronic structures. The scientific terms for these are wave mechanical tunneling, quantum mechanical tunneling, and the tunnel effect. Quantum tunneling was developed from the study of radioactivity, which was discovered in 1896 by Henry Becquerel. It is the study of what happens at the quantum scale. This process can be directly perceived, so much of its understanding is saved by the microscopic world.
Which animals have two rings? Birds have two rings.
बैठ इधर.
दीदी आप ये बोलो कौन आया ना उसका उसके which animal has two rings and two
Radioactivity.
bird have two rings and two legs सही दिया ना दीदी इसके आगे दीदी लाया कर ला ले रहा है चल चल दूरा पर चल आकर पूरा दर्शन की बात चल पूरा दीदी हेलो
Radioactivity which was
हेलो
directly perceived,
की है
so much of its understanding is served by the microscopic world, which classical mechanics can adequately explain. Particles in that realm are understood to travel between potential barriers as a ball rolls over a hill in our world. If the ball does not have enough energy to surmount the hill, it comes
ले आ खाली छौरी का पारी नहीं गई
predicates that particles that do not have enough energy to climb the hill, it will not be able to reach the other side. In quantum mechanics, these particles can, with a very small probability, tunnel to the other side, thus crossing the barrier. The reason for this difference comes from the treatment of matter of quantum mechanics as having properties of waves and particles. The waves functions of a particle summarize everything that can be known about a physical system. Therefore, problems of quantum mechanics center around the analysis of the wave functions for a system using mathematical formulations of quantum mechanics such as the Schrödinger equation. The wave functions can be solved for this is directly related to the probability density of the particle's positions, which describes the probability that the particle is at any given place. If the limit of large barriers, the probability of tunneling decreases for taller and wider barriers. Hence, the probability of a particle on the other side is non-zero, which means that cross the high barrier sometimes and experimentally it is also verified.
सकाळी क्रिकेटचा सामना झाला. साले क्रिकेटच्या सकाळी क्रिकेटचा सामना झाला. दीपालीने गोलंदाजी केली.
2.5 Practical value of quantum mechanics. The equation developed by Heisenberg, Schrödinger, and their colleagues given a glimpse into the nature of reality, but that's not all. They are also essential tools of modern work in key areas of particle technology, including the electrons. Viewers using a read this text. Thousands of physicists use the equations of quantum mechanics every day to understand and improve computer components, metals, lasers, the properties of chemicals, and on. Many important physical effects from fluorescent
इंग्लिश में बोल.
fluorescent lights to the shape of a snowflake can't be understood at all without quantum mechanics. Even the uncertainty principle isn't merely philosophy, it predicates real properties of electrons. Electrons jump at random from one energy state to another state which they could never reach except that their energy is momentarily uncertain. This tunneling makes possible the nuclear reactions that power the sun and many other processes. Physicists have put some of these processes to practical use in microelectronics. For example, delicate superconducting instruments that us electron tunneling to detect tiny magnetic fields are enormously helpful for safely scanning the human brain. Quantum theory is used in a huge variety of applications in everyday life, including lasers, CDS, DVDs, solar cells, fiber optics, digital cameras, photocopiers, barcode readers, fluorescent lights, LED lights, computer screens, transistors, semiconductors, superconductors, spectroscopy, MRI scanners, lasers, superconducting devices, etc. By some estimates, over 25% of the GDP of developed countries is directly based on quantum physics. It even explains the nuclear fusion process taking place inside stars. Thus, the effects of quantum mechanics are important in all branches of science. Quantum mechanics is used to understand phenomena like radioactivity, chemical bonding, semiconductors, solid state microchips, electronics, subatomic physics, radiation from black holes, and many others till 2009.
Behind the basket.
2.6 Final remarks on human intuition. In spite of his weirdness, we have a theory which accounts for all of our experimental results. It correctly predicates the results of double slit experiments with photons or electrons, and it correctly predicts that in the case of normal light beams or particles. In fact, thousands of other experiments have been performed since quantum mechanics was developed, and they have continually supported its predictions to a struggling level accuracy. This theory seems to apply to every process occurring between any kinds of matter or energy in the universe. Felder 1998. No one really understands this theory of quantum mechanics, but quantum mechanics can be used to successfully predicate experimental results. So, quantum mechanics leads to a new ways of looking at existence and reality. The modern view of quantum mechanics states that Schrödinger's cat or any microscopic object does not exist as superpositions of experiments due to the occurrence of Pristine wave functions is current that is undisturbed by observation, but Schrödinger's cat is not a pristine wave functions. It is constantly interacting with other objects, such as they are molecularless in the box or the box itself. Thus, the microscopic object becomes decoherent by many atomic interactions with its surrounding environment. Decoherence explains why we do not routinely see quantum superpositions in the world around us. It is not because quantum mechanics intrinsically steps working for objects larger than some magic size. Instead, microscopic objects such as cats are almost impossible to keep isolated to the extent needed. A prevalent decoherence microscopic objects in constant are more easily isolated from their surroundings, so that they retain their quantum secrets and quantum behavior. Organ 2011. It does seem to make sense, but another school of thought says, why should it make sense? My object becomes decoherent by many atomic interactions with an decoherence explains why we do not routinely see quantum superpositions in the world around us. It is not because quantum mechanics intrinsically stops working for objects larger than some magic size. Instead, microscopic objects such as cats are almost impossible to keep isolated to the extent needed to prevent decoherence. Microscopic objects in constants are more easily isolated from their surroundings, so that they retain their quantum secrets and quantum behavior. Organ 2011. It does not seem to make sense, but another school of thought says, why should it make sense? After all, humans evolved in a world of normal objects, and we developed a facility called intuitions that help us survive in the world by helping us predicate the efforts of our action. That physical in, intuition was and is a great asset, but perhaps it should not be too surprising that it becomes a liability when we try to apply it to areas that we didn't evolve for. Quantum mechanical laws generally only have measurable effects when applied to things that are too small to see, so we never evolved an understanding of them. So they seem Bajar, Felder and Felder 1998. In fact, at roughly the same time, the quantum mechanics first began to suggest that very small, this dirtier intuition, Einstein was proposing his special theory of relativity, which shows that very first things defy our intuitions, and then his general theory of relativity, which concerns the odd behavior of very big things. Felder and Felder 1998. It seems that more and more the only way to understand the world is to apply the math and stop trying to understand what's actually going on. If you look at it like this, it seems that physics is not bad and in comparable, because it describes something completely different from everyday reality. It is wide and incomparable precisely because it describes the world we see around us, present and future. 6 number 5, 7